Thank you for the introduction and thank you everyone for being here. So yeah, I arrived here in Bologna and I'm still working on some projects that I started with the group in Chile. And the general topic is that of galactic archaeology. And I work more on the field of dynamics and kinematics and try to get all the possible information that we can from the observations that we have to understand the structure of our local universe. So this is kind of the summary of the talk that I will give, and I will have kind of a bit of random image at the start because it's difficult to select images that represent orbit integration because it's just orbits. I mean, so there you go, orbits. But I will try to explain to you why orbital integration is important, what it is and how it is done, what are the sanity checks that we can do to be sure that we are doing it right, and then discuss my work, both recent, current, and future. So why orbital integration? Orbital integration is extremely important because while it sits at the crossroad between observations and simulations, because you need observable data, but also you need a model that you have to apply to this observable data. It's useful because it expands the parameter space of what we know based on the observation. So you take the phase space information, positions and velocities of observed tracers. It can be stars, globular clusters, can be anything that orbits. And then you derive their orbital history, and you can use it to study the dynamics, to study the structures and substructures that are in our local universe, in our Milky Way, for example. And the orbital history allows you to also study the assembly history of the Milky Way, which is a kind of a hot topic at the moment. And these are just two examples, one from a paper from a PhD student in Chile, Julio Olivares Carvajal, where we use my integrator to have a selection on the stars that spend more time in the bulge region of the Milky Way. And the other is one of the many examples of the angular momentum versus energy plot that's used widely to explain the assembly history of the Milky Way. So, okay, what is orbital integration? The assumption here is that in first approximation for order zero, what moves things in the universe is gravitation, is the gravitational force. And this allows us to start from the today observations, the observation of the position and velocities today of an object, and reconstruct by applying a model of the density distribution that these objects inhabits to reconstruct this orbit, to see where it has been or to see where it will be. This is because orbit integration can be used in our field, in galactic archaeology, is used to look at the past, but in other fields in astronomy is used to look at the future, so to do forward orbit integrations. And this is one of the most egregious examples in recent time, where we sent a satellite against the moon of an asteroid to try and deflect the trajectory of a double asteroid system. And this is just an example of forward integration, but I don't do this. I do the galactic stuff, which is backward integration. And there are some things that you need to do orbital integration. The first thing is that we don't use, luckily we don't use pen and paper anymore. We use computers, and you need, for computing, I'm sad for Python because it has widespread use, but to do orbital integration, since you need to do a lot of repetitive actions, so the same equations need to be computed over and over. The languages, the computing languages that are more close to machine code are much better at it. So that's why most of the integrators use either C or Fortran or C++, one of these, or the many Fortrans that exist. There are some like GalPy that are Python, but usually it's a Python wrapper for a C package. You start with your initial conditions, which are the observables, and then you use an algorithm to go from the observables to the expressions for the acceleration, so the expressions of the force that's acting on your tracer. And then you want to know this force at an arbitrary point in time. And to get to that arbitrary point in time, you start computing a series of, you basically just compute the entire orbit. So step by step, designing a time step, you start computing the acceleration every time step until you get to the decided time. And obviously, as I was saying, you need a model for the density distribution that is the main protagonist of orbital integration, which can be the galaxy, like the Milky Way, or it can be the solar system or any other kind of system. So you take all of this, you put in your equations, you mix all the ingredients, and then you get something. And how do you decide if what you get is something that has a sense or no? When you have the sun orbiting the Milky Way, or you have the planets orbiting the sun, in first approximation, everything is very simple. When you have thousands, tens of thousands, hundreds of thousands of stars, it's more difficult to know exactly what to expect when you do the orbital integration. That's why you need a system to detect the failures. For example, there are two clear failures here. One is here. One is here, which is basically a star that went too close to the black hole and so received an energy kick and just went away for the rest of integration. And the other side, on the other side, there is another case where there was something wrong in the equation and in the equations, and the star was gaining and losing angular momentum where it should have either gained or lost angular momentum. And this is because in orbital integration, I mean, in the problems that we face, that we try to solve with orbital integration, we need some sanity checks, some conserved quantities that we can check to detect these kind of failures when they are not as obvious as these ones. And these kind of sanity checks are, for us, are represented by the integrals of motions. So usually when you have a static potential, so your density distribution is not changing over time, you can check the conservation of the total energy and the conservation of the angular momentum, the total mechanical energy and the conservation of the angular momentum. And the case up here is the case of the star before, when the angular momentum was not conserved, when it should have been conserved. And so the orbit of the star was completely wrong. In most cases, your algorithm is supposed to conserve the energy if the potential is static. In other cases, which is the case where with which I work mostly, you don't have a static potential, because in my case, I use a rotating bar for the Milky Way potential. And then you don't conserve the mechanical energy and you don't conserve the angular momentum, but you conserve another thing, which is the Jacobi energy. And as you can see, conservation here is a term with like a wide meaning. You don't get zero in the ratio, but you get an oscillations around the zero, which is good enough for orbital integration purposes. So now let's move to the problems that we try to solve. The Milky Way. The Milky Way, as far as structure, it's quite complex. We know it has several components, be they gas, stars, dark matter, and there are several models that reproduce the Milky Way and its density distribution. And all these models are a mix of this kind of all these substructures. Some things that people usually ignore are the streams and remnants in the stellar halo, because they are not gravitationally significant enough to complicate your model to include them, and so it's very difficult to include them, because they don't have their mass is very low, and usually they are distributions very spread out in space, so they don't impact the density, the overall density distribution too much. The gas spiral arms also are something that's always overlooked. But strangely enough, in most of the models commonly used to do orbital integration, also the rotating bar of the Milky Way is overlooked. And this is strange because it's been a few years, a few decades that we have convinced ourselves that the Milky Way has a rotating bar at the center. So just to give a few examples, most of the, not most, but the most used models for the Milky Way are the ones from BOVI 2015, is the Milky Way Potential 2014, a bit confusing the name. That's the basis for GalPy, for the integrations in GalPy. And another one that's used almost always is the Macmillan 2017. And these two models are static models. The potential don't include anything that changes over time. And they include some of the substructures that I was pointing out before. There are some other models that don't see much use. They usually are restricted to the research group that developed them, like the Rossi 2015 model. But they also don't have prescriptions for all the components of the Milky Way that are up to date with the current constraints that we know. So what I did was to develop a new model. It's not new, like an up-to-date model. There is nothing new there. Everything is already known, but I just put together the components differently from what it's done right now. And this model has the dark Mattarello, Navarro-Franke-White dark Mattarello, and then several Miyamoto Nanagai disks, two that represents the stellar components, two that represents the gas components, and then a composite barge that's made by a rotating long Murali bar and a spheroid. And also I have the central black hole, but for most purposes, the central black hole doesn't do much. It just, when stars get really close to it, it does something, but most of the time it doesn't do anything. And just to show that the model is not completely made up, on the side, you have the circular velocity curve of the Milky Way, and the red dot is the sun, so the velocity of the sun. And this is just to show that the model, without too much tampering and without too much fine-tuning of the parameters, can reproduce the circular velocity curve of the Milky Way. Now I talked about the algorithm. Let's talk about the algorithm that I use. As I was saying, you need to conserve something at least before you start mucking around too much with the density distribution and having too many things that change over time. Because you need to check that your code is properly doing its job, and you need to check that the errors, the numerical errors, especially in the approximation that's been done during the integration, it's kept in check. So my code is written in C, and I use the leapfrog algorithm, which is a modifying form of a Verlet integration. Basically, it works with this scheme over here. So at each time step, you compute the velocity at the half time step, then you compute the position, then you do the very expensive calculation to compute the acceleration, which is the main point, the main quantity that you want to compute each step. And then you update finally the velocity to the final value for that step. I decided to use the leapfrog because it's quite simple, it's efficient, and also because it's symplectic and time reversible. It means that if my potential is well behaved, so for example, even adding a rotating bar to the potential is not a big problem for it. If my potential is well behaved, if the potential changes over time in a precise manner, I can do the forward integration of something and then take the last time step as the new initial conditions, go backward and obtain the same results, obtain the results as a result what I started with. And also, as you were seeing in the slides before, it conserves the principal conserved quantities. Like if I don't add the bar to the potential, it conserves the energy and the angular momentum. And if I do add the bar, it conserves the Jacobi integral. And then as far as data goes, I've used VVV survey, Gaia, Apogee. Everything is good as long as I can work with all the 6D information. So proper motions in the sky, radial velocity, position, and distance, then the code can work. And now to discuss some results. This is the same plot, another rendition made by me as the plot that I showed at the start with all the substructures that are in the Milky Way, the merger history of the Milky Way, and I have highlighted a few. And the study of the assembly history of the Milky Way has really expanded now that we have very surveys that give us a enormous amount of data, because it allows to do statistical studies on the stellar population's presence in the Milky Way. And to start, I use the distinction of clusters and their progenitor, globular clusters and their progenitor. Each point on the board is a globular cluster. That was made by the seminal work by Davide in 2019, which was the first one to actually publish a list of which progenitor each cluster belonged to. We are talking about clusters in the Milky Way, globular clusters in the Milky Way. And as you can see, there are a lot of clusters that don't have a color, that are black. And this is because in recent times, we kept discovering or confirming some clusters. And these clusters are usually missing from the common divisions and categorization that's been done. So what I'm doing is go and look at some of the most recent or most interesting ones and try to pin them to one of the progenitors. And this is useful, one, to know which clusters come from which progenitor, and two, because the number of globular clusters that a progenitor has or can give an information on the nature of the progenitor, its mass when the accretion happened, and also because if we can study, usually we can study the globular cluster better than other type of populations. So it's useful to know which globular clusters to study for different progenitors. So let's take a look at some of the more recent globular clusters. The Los Granes, as they are affectionately called, are 5 globular clusters, first identified as candidate and then confirmed by Felipe Gran, who was a student at Pontificia Università Católica de Chile. He published 2 papers in 2022 and 2024. And these clusters still have not found properly a family, still have not found a progenitor. And I use my code to integrate their orbit and derive all the orbital parameters that I can, and see if I can give an answer to the question, who is the progenitor of these globular clusters. For what regards Gran 1, he sits very nicely in the potential well, is a well-behaved globular cluster from the bulge. For the others, it's not so simple, because while they might be in some regions of the angular momentum energy space where we think the progenitors are well defined, in reality, there is a lot of overlap in these regions between the different populations and the different merger events. So we need to look not only at the energy and the angular momentum, but we need to look at also at other dynamical parameters to try and pin them. So this will require some explanation. This is a plot that I made inspired by the work of Malan 2022, where I think you were one of the authors too. This uses the actions. The actions are like far removed cousins of the angular momentums, and they give us information regarding the type of orbit that an object had. So something very prograde will be on this side of the plot. Retrograde objects will be on the other side. If something is down here, it will have a radial orbit, up there a polar orbit. And this gives you information because, as you can see, while they are very scattered, the clusters that belong to some of the structures tend to cluster a bit in some spaces. So all the clusters from the disk are here, or the clusters from the Gaia Enceladus sausage are kind of here. So we can use this plot and other of the parameters to try and pin the clusters down. And this is what I did. So as we can see, I was saying gram 5 could have been a globular cluster from the bulge or from the low energy or Kraken or Koala event. You can call it whatever you want. There are several names for that event, but its dynamics is that of globular clusters of the bulge. Gram 2 could have been either from the Jess or from the retrograde family, but its dynamic says that it's from the retrograde family. And then we're left with gram 4 and gram 3, which are still uncertain because gram 3 can be either from the big family of retrograde events like Sequoia, Arjuna, and Itoi, or it can be the first confirmed globular cluster of Tamnos, which is another of the merger event, just with a little bit of lower energy. And then there is gram 4, which is uncertain between the Helmi streams and Sagittarius. Gram 4, these are plots from the same paper as the start, Naidu et al. 2020, which are very useful because they use other parameters, so the angular momentum in different directions, to try and constrain the different families. And as you can see, gram 4 is not kinematically and dynamically a member of Sagittarius, and most probably is a member of the Helmi stream. And gram 3 is probably a member of Tamnos due to his pericenter, apocenter, and eccentricity. As you see here, these are a lot of different parameters. So we move in a parameter space that's very varied. And but this is both the power, the beauty, and the problem of orbital integration. You have to look at a lot of things to try and decide how to assign the different ones. The different clusters to the progenitor. Some other clusters that I'm looking at are some of the Palomars. As you can see, there is a new structure, which is the Aleph, which is very, very progred over there. And there are some clusters that have been assigned years ago to the disk, but now we believe there is a building consensus that there might be another structure called Aleph. So these clusters might belong to the Aleph and not the disk. And that's it. So this is my work. I make things spin in the computer and then look at where they end up. And this is just the inclusion of the bar is just one step. There are other things that I'm working right now with the group here, like the inclusion of the LMC, which has quite a big impact. We know from the literature already, especially from the work of Garavito Camargo, that it has a huge impact on the dark matter distribution, and we want to check what impact it has on the dynamical parameters of the clusters and stars in the Milky Way. And there are a lot of different things that you can explore doing orbital integration. And so, yeah, that's why I'm here. Thank you.
Thank you very much. Questions? I might. Oh, okay.
Very nice talk. I was wondering about the mass evolution of the cluster that you are estimating, and tidal losing mass because of tidal shocks and what effects on the reconstruction of the orbit.
At the moment, like everyone in the literature, I'm not including dynamical friction receipts, but you can include the dynamical friction. The problem with dynamical friction, which I might overlook in the case for the LMC, is that it's a non-conservative process. So it completely destroys any integral of motion that it destroys the conservation of the integrals of motion that you have. And the computational problem of adding dynamical friction is that it depends on the velocity. So the advantage that the leapfrog had over other type of integrators is that you have to compute the quantities needed to compute the acceleration only once every time step. If I need to compute the velocity every time, I need to compute the total acceleration, the total force applied on a object. It becomes computationally more expensive. It's certainly something that needs to be done, especially for clusters that are very close to the bulge. We expect there are several clusters that end up very close to the bulge that are kind of peculiar for one reason or another, for their dynamics, for their metallicity. And we expect that it is because due to the dynamical friction that they experience during their orbit, they belong to some other progenitor or had more interesting past. But what we see now is very influenced by the fact that we are not looking at the original mass of the cluster.
Other questions?
What's the consensus between your results, so your associations to these systems, and I don't know, maybe other studies, are there something other present in literature? And in case of negative answer, where could be the differences between associations?
So let's go. So I'm still working on all the parameters for all the clusters, and one important thing to do, not computing them, I have them, but looking in detail at each of them. But one important thing to do is that this is a completely dynamical study. Another different phase of the problem is looking at the chemistry and looking at the ages of the clusters. This is information that I mostly don't have. For some of the clusters where I'm very convinced of my answer, I go look at the metallicity or available data in the literature. And most of the time, there is a consensus with the literature. Where there is not is usually these new clusters, like the grand family of clusters or some of the VCL. And most of the time, since these clusters are clusters that have been observed in the bulge region of the Milky Way, one of the possible differences is that people are not including the effect of the bar. So the orbital reconstruction is not done with a proper or more in detail or more up-to-date potential.
We have a question from from online. Let's see. Okay, you can ask the question.
Okay, can you hear me?
And not, well, just 1 sec. Please speak.
Now?
Yes, better. Thank you.
Okay, thank
Go
you.
ahead.
My question is about the fact that, as you mentioned, the parameter space is huge because you are including several components in your models. And so similarly to maybe part of the previous question, I was curious how much in the literature these models, the choice of the components is homogeneous, in the sense that you can compare your results to other that maybe didn't include a disk, as you mentioned, or a bar, and so on.
Yeah, so for what concerns my model, I feel so stupid always calling it my model, but whatever. For what concerns my integrator, basically the only difference I have to a normal Macmillan 2017 is the rotating bar. And a bit the bulge, the spheroidal part of the bulge, because all the other components, the dark material and the disks, are very similar to a classical static Macmillan 2017 potential. The potential from Bovi, it's very different from all of this because it's kind of a very simplified potential that worked quite well, or at least worked quite well in the past for the halo, but is not really made to look at things that are either in the bulge or there are on very radial orbits that go into the bulge, because it has a very small spherical bulge, only one disk, and the dark material. I'm not aware if there has been an update of the Milky Way potential 2014 to more modern stuff. It's quite old, so what we know about our galaxy changed a lot since 2015. And usually the disks are not the problem. The disks, be they stellar or gaseous, the overall mass and this distribution is usually the same. The dark material also is usually the same, but there is the notable exception of the Rossi potential, which has a huge dark material, something like 3.5 times 10 to the 12 solar masses. But yeah, most of the differences are in what you use as a bulge. Does that?
And do you think that okay, and so do you think that from the purely dynamical point of view, this can affect this choice can affect for example, the attribution of these clusters to a stream or another, or in general, the result is quite the same? I mean,
the problem is that, well, it's one of those it depends cases. In most cases, it will not affect, because for example, most of the clusters that we identify as bulge clusters are so deep in the potential well that they are just bulge clusters, or maybe they are from the old metal poor earth of the Milky Way, the aurora populations, these very old mergers where the dynamical information is completely lost. In other cases, where kind of the border region where you have all the low energy family of clusters, low energy, Kraken, Heracles, Koala, there are several names for these structures. It can be more important because maybe the clusters are on radial orbits that respond differently to the presence or absence of a bar and things like that.
Yeah. Okay. Thanks.
Thank you. We have time just for one quick question. So, Raffaele.
Mine is more like curiosity. You said you used leapfrog, which is symplectic and of the second order. There is any reason why not using a higher order integrator, like of the fourth order, like a forest root or?
No, for the moment it's just a matter of simplicity of the integrator, but it can be expanded to use an higher order. Yeah. All obviously not Runge-Kutta because there are no symplectic, but yeah.
Order integrators like forest root, which is of the fourth order.
There is the possibility to change the code. Yeah.
Okay. Thank you very much. Let's thank the speaker again.